When AI needs to react instantly, whether it's detecting objects in a busy intersection, tracking shoppers in a retail store, or monitoring assembly lines, you need a platform that can process multiple video and sensor feeds in real time. NVIDIA's DeepStream SDK is built exactly for that. It's a GPU-accelerated streaming analytics toolkit that connects cameras, sensors, AI models, and message brokers into a single low-latency pipeline, perfect for deploying vision AI at scale. In this lesson, we'll unpack what DeepStream is, how it works, and why it's the backbone for edge-to-cloud video analytics. DeepStream is NVIDIA's end-to-end framework for processing high-volume video and sensor streams with AI. It uses GPU acceleration to decode, process, and analyze streams in real time. You can run it on Jetson edge devices, NVIDIA desktop GPUs, or cloud GPU instances. DeepStream integrates natively with TensorRT and Triton, so you can deploy optimized models from TAO or OnNX without rewriting your pipeline. It's also designed for multi-stream scenarios. Think dozens or even hundreds of camera feeds in parallel. Under the hood, DeepStream builds on the GStreamer framework, which means your AI pipeline is a sequence of pluggable elements. These elements handle decoding incoming streams, pre-processing frames, running inference, post-processing results, and sending output to the next stage. The SDK supports video streams, still images, LiDAR coin clouds, and IoT sensor input. Using NVIDIA's NVDEC and NVENC hardware blocks, DeepStream can decode and encode streams with minimal CPU overhead. Finally, you can send your AI results to a dashboard, database, or message breaker for further action. DeepStream is model agnostic, but TensorRT optimized models will run fastest. You can import models from TAO Toolkit or use OnNX models exported from TensorFlow or PyTorch. Pre-trained models for object detection, image classification, or segmentation can be dropped in with minimal configuration. You can even chain multiple AI models in a single DeepStream pipeline. Say, run an object detector first, and then a classifier on each detected object. DeepStream is built for scalability and speed. It can run AI inference on multiple streams simultaneously, batching frames to keep the GPU busy without adding noticeable latency. It supports event-driven messaging via Kafka and MQTT, enabling quick integration with enterprise workflows. For tracking, DeepStream includes GPU-accelerated algorithms like NVDCF and KLT to follow detected objects across frames. And you can overlay analytics directly on live video feeds, bounding boxes, labels, confidence scores before sending the output. You can deploy DeepStream in several ways. On Jetson devices like the Orin or Xavier for edge AI processing, on GPU-powered servers for aggregating multiple sites, or in the cloud for massive scalability. For DevOps integration, DeepStream supports Kubernetes and Helm charts, and the official containers are available on the NGC registry. This means you can build once and deploy anywhere, edge, on-prem, or cloud. DeepStream powers real-world AI applications across industries. In smart cities, it's used for traffic flow optimization and license plate recognition. In retail, it drives footfall analytics and shelf inventory tracking. In industrial settings, it detects defects in products on assembly lines. In healthcare, it can monitor patient safety and ensure PPE compliance. And in IoT and robotics, it supports navigation and obstacle detection. In a modern AI pipeline, DeepStream sits right at the data ingestion stage, pulling in video and sensor feeds, decoding them, running inference, and producing results in milliseconds. It integrates directly with Triton Inference Server for serving models and can feed its results to real-time analytics dashboards or control systems. It also supports stream-to-cloud setups, sending pre-processed data to cloud platforms for long-term storage or further analysis. And when paired with RAPIDS, it enables GPU-accelerated analytics on live data streams. DeepStream is the bridge between real-world data and AI insights. whether you're building smart city infrastructure, autonomous machines, or retail analytics systems. In the next lesson, we'll design real-time DeepStream pipelines tailored for surveillance, retail, and IoT use cases, so you can see exactly how to connect these pieces into production-ready systems. Now that we understand what DeepStream can do, let's make it real. In this lesson, we'll walk through how to design real-time AI pipelines for 3 high-impact domains: surveillance, retail, and IoT. You'll learn how to connect video or sensor inputs, process them with AI, and route the results to dashboards, alerts, or automated control systems, whether running at the edge, on premises, or in the cloud. Think of this as your blueprint for deploying production-grade, low-latency AI. At its core, every DeepStream-based real-time AI pipeline follows the same sequence. First, ingest the input. This could be an RTSP camera stream, a pre-recorded video, or even a LiDAR or IoT sensor feed. Then, decode and pre-process the data to match your model's expected input, resizing frames, normalizing pixel values, and converting formats. Next, run the inference step with a TensorRT optimized model for maximum performance. After inference, post-process the results, drawing bounding boxes, counting objects, or filtering by detection confidence. Finally, output the processed data to wherever it's needed: real-time dashboards, cloud databases, alerting systems, or even actuators that trigger physical actions. In a surveillance use case, inputs usually come from multiple IP cameras streaming over RTSP. You might chain an object detection model with a license plate recognition model for vehicle tracking. To maintain object identities between frames, you'd use a tracker like NVDCF. Processed video feeds can be displayed in a control room dashboard, while metadata is stored in an event archive for compliance or investigations. For real-time alerts, like detecting a restricted zone breach, DeepStream can publish events to Kafka or MQTT, which downstream systems consume to trigger notifications. In retail analytics, ceiling-mounted cameras feed into the pipeline. You might use a people-counting model combined with dwell time estimation to understand customer behavior. DeepStream can generate heat maps showing which areas of the store get the most traffic and when. The results feed into a business analytics dashboard and can be correlated with POS transaction data or inventory levels. This allows store managers to optimize shelf placement, staffing schedules, and promotional displays in near real time. For IoT and Edge AI, you might combine a camera feed with IoT sensor data, like temperature, vibration, or LiDAR scans. An anomaly detection model could monitor for unusual patterns, while a predictive maintenance model flags potential equipment failures. On-site processing can run on Jetson Orin or Xavier devices for low-latency inference without relying on the cloud. Results can be sent to cloud systems via MQTT or REST APIs, or trigger local actions like shutting down a machine or sounding an alarm. As demand grows, you'll need to scale. DeepStream supports multi-stream ingestion with batching so the GPU stays busy. Pipelines can be distributed across multiple GPUs in a single server, or across multiple nodes in a Kubernetes cluster. Helm charts make orchestration straightforward, and you can dynamically load balance streams between instances. For serving AI models at scale, integrate Triton Inference Server so you can easily switch models, run A/B tests, or deploy updates without downtime. DeepStream provides NVDS performance APIs that let you monitor frames per second, per stream latency, and more right from your application. You can enable inference batching for better throughput, but be mindful of latency. Adjusting resolution is another easy lever. Lower resolution increases speed, but can impact accuracy. For system-level profiling, tools like Nsight Systems give you GPU and CPU utilization insights. If you need real-time aggregation of results, say, for a dashboard, RAPIDS can process metadata streams on the GPU without slowing your pipeline. Whether you're monitoring a city, optimizing a retail space, or managing industrial IoT systems, the basic principles of pipeline design stay the same: ingest, process, analyze, and act in real time. In the next lesson, we'll look closely at RAPIDS, NVIDIA's GPU-accelerated data analytics suite, and see how it supercharges the post-processing and analysis stages of your real-time AI pipelines. Real-time AI doesn't stop at detection. Once your DeepStream pipeline has generated metadata, like object counts, classifications, or sensor readings, you need to process and analyze that data instantly to make it useful. That's where RAPIDS comes in. RAPIDS is NVIDIA's open-source suite of GPU-accelerated data science libraries that lets you run Pandas-style analytics, SQL queries, and even machine learning entirely on the GPU. In this lesson, we'll see how RAPIDS integrates with DeepStream so you can handle massive streaming datasets with sub-second latency. RAPIDS is a collection of Python libraries that run entirely on the GPU. It's built on CUDA, so even operations like joins, filters, and aggregations run in parallel at massive scale. The core libraries are CUDF for data frame operations, CUML for machine learning, and CUGraph for graph analytics. What's great is that RAPIDS mirrors the APIs of popular CPU-based tools like Pandas, scikit-learn, and NetworkX. So the learning curve is small, but the speedups are huge. For AI pipelines, RAPIDS means you can process and analyze data as fast as you can generate it. When DeepStream produces metadata, like object detections, timestamps, and classifications, you want to process that information without bottlenecks. By using RAPIDS on the same GPU as DeepStream, you avoid costly CPU-GPU transfers and can run analytics at streaming speeds. This lets you handle millions of events per second, perform complex joins and aggregations, and feed the results right back into your AI pipeline, triggering decisions in milliseconds instead of seconds or minutes. The CUDF library is the heart of RAPIDS. It's like Pandas, but on the GPU, and perfect for manipulating DeepStream metadata. CUML gives you GPU-powered machine learning, great for real-time clustering, regression, or anomaly detection. CUGraph handles graph problems, like tracking relationships between objects or detecting communities in a network. For scaling across multiple GPUs or nodes, Dask CUDF distributes the workload, and Blazing SQL lets you run SQL queries directly on GPU data frames without moving the data to the CPU. Imagine a smart city scenario. DeepStream detects vehicles and pedestrians from dozens of traffic cameras. The detection metadata flows directly into a QDF data frame, where we can group by intersection and count vehicles in real time. Using QML, we run a regression model to predict congestion before it happens. Those predictions are sent to the city's traffic control system, which can adjust light timings to prevent bottlenecks, all happening automatically and continuously. The performance uplift from RAPIDS is huge, anywhere from 10 to 50 times faster than CPU-based Pandas or scikit-learn, depending on the workload. You can process millions of rows in milliseconds because all operations stay in GPU memory. And with Dask QDF, you can scale horizontally across multiple GPUs, either on a single machine or across a cluster. This makes RAPIDS a perfect match for edge-to-cloud architectures, where data starts at the edge but needs to be processed at scale in the cloud. Integrating RAPIDS with DeepStream is straightforward. Use the DeepStream Message Converter plugin to export detection metadata as JSON or Kafka messages. Those messages can be ingested directly into a CUDF data frame for processing. From there, you can filter, join, and aggregate data in real time, or run machine learning models in CUML. You can even execute GPU-native SQL queries in Blazing SQL. The results can be sent to dashboards, alert systems, and so on, or directly back to control systems for immediate action. RAPIDS transforms DeepStream from a real-time inference engine into a real-time analytics powerhouse. With all processing happening on the GPU, you can turn raw detections into actionable insights almost instantly. Next, we'll explore how to integrate Kafka, MQTT, and other stream processing tools to move this data seamlessly across systems. Real-time AI pipelines don't exist in isolation. They need to communicate with the rest of your systems. Whether it's sending object detection alerts to a control room, pushing sensor readings to the cloud, or streaming analytics into a dashboard, Message brokers like Kafka and MQTT make it possible. In this lesson, we'll explore how to connect DeepStream and RAPIDS with enterprise and IoT messaging systems, so your AI insights can move instantly from the GPU to anywhere they're needed. Messaging systems are the glue that holds modern AI pipelines together. By using brokers like Kafka or MQTT, you decouple the AI processing from the systems that consume the data. This enables event-driven architectures, where detections or analytics trigger immediate actions. Multiple consumers can subscribe to the same data, dashboards, cloud services, or databases, and you can scale to thousands of sources without overwhelming the AI layer. With built-in buffering and replay, message brokers also improve reliability and fault tolerance. Apache Kafka is a distributed publish-subscribe platform built for scale. It can handle millions of messages per second, making it ideal for large enterprise streaming workloads. Kafka guarantees ordering within a topic partition, which is critical for time-sensitive analytics. Messages are persisted to disk, so you can replay historical data for analysis or debugging. In AI pipelines, Kafka acts as a high-speed highway for moving detection events, sensor readings, and analytics outputs to other services. MQTT is a lightweight messaging protocol designed for IoT and embedded systems. It uses a publish-subscribe model like Kafka, but with very small message sizes, perfect for low bandwidth or unreliable networks. Devices publish to topics, and subscribers receive only the messages they care about. This makes MQTT the protocol of choice for edge AI deployments on Jetson devices or embedded sensors that need to send frequent updates without draining bandwidth or power. DeepStream has built-in support for Kafka, MQTT, and other brokers via the NVMSG broker plugin. This plugin can take detection metadata, like object type, coordinates, confidence scores, and publish it in JSON format to the configured broker. You can choose the broker type in the DeepStream config files, set authentication credentials, and define the topic names. Once published, the data can be consumed by RAPIDS for further GPU analytics, fed into a visualization dashboard, or ingested by a cloud application for decision-making. Messaging is just the start. You often want to process the data while it's still in motion. This is where stream processing frameworks like Apache Flink or Spark Streaming come in. They let you filter, aggregate, and enrich messages in flight, so you can trigger alerts or send control signals instantly. You can even run machine learning inference directly in the stream processing layer for additional context before data ever hits storage. And since these frameworks run in Kubernetes, they can scale out dynamically with your workload. Let's take a retail loss prevention example. DeepStream detects suspicious activity in-store and sends metadata to the Kafka topic retail alerts. A stream processor listens to that topic, filtering only high-confidence detections to avoid false alarms. Those filtered events are pushed via MQTT to an in-store security officer's tablet, while the raw data is archived in a cloud database for auditing and training future models. A good rule of thumb: use Kafka for high-volume, large-scale enterprise streaming where ordering and replay matter. Use MQTT for lightweight IoT updates from edge devices. Keep your messages as small and structured as possible. JSON is easy to work with. Always secure your brokers with authentication and encryption, like TLS or SASL. And finally, monitor your brokers using native tools like Kafka Manager or MQTT broker logs to ensure reliable performance. By connecting DeepStream and RAPIDS to Kafka or MQTT, you can push AI insights anywhere, in real time. From massive enterprise deployments to low-power IoT devices, these messaging systems make your AI pipelines truly event-driven. In the next lesson, we'll put all this into action with a hands-on lab, creating a DeepStream pipeline that runs on a Jetson Nano and streams detection events to a message broker.